Great value mean? That's so the great value thing is kind of an old joke on this course. If you go to Walmart, one of their generic brands is the great value brand.
Yeah.
And so the original joke was that this course was offered as an independent study for Quantum 1 back in spring of 2020. And the joke that it was great value was because the semester, like the year before that, we'd had it and there were like 14 people in it. So we just had a normal course. And the year after that, there were 10 people. So we had a normal course. But we had 2 people who needed it to graduate that semester that somehow missed it the previous semester, largely because they swapped majors around. And so we were joking because it was an online version of it. Like it was an independent study version. And the instructions given to me from the chair at the time, it was still Dr. Menon, but the instructions he gave to me were just give them a copy of your notes and have them come meet with you like once a week to go over them. Which is fine, but it's also like not not really taking the course. That sounds like somebody's here. Hang on. Colin, you here?
Yeah, I'm here.
Okay, cool. You got in. Good. So the great value joke was that the students who were still here that did not take it that way had one student was named Sam Gangley and his friend Nick Johnson, both are in Florida these days. But they joked because they were friends with one of the guys that was taking it. They joked that he was getting like the generic bland Walmart version. And so we've been calling it Great Value Quantum ever since.
Okay.
And so it just kind of stuck when James and Ash took it last semester, or last spring, which, they got a real version of the course. We had meetings, we did notes just like we're doing here, but it's just become the joke that anytime that it's offered not in person in the classroom, it's the great value version. In part also because, frankly, the reason why we do it this way is because Troy is trying to do stuff on the cheap.
Yeah.
All right, so that, I guess that covers our mandatory story for the day. Let's actually get into the notes. I know you guys have places to go. I found where we were. We've got continuous superposition. That's and here's the figure that we had left off on in case anybody needs it. But we're looking at expectation We're looking at expectation values today. And then going from there. So let's basically try to note that this is, we have a quantum mechanical wave packet. We're trying not to do anything relativistic. Okay, that is beyond the scope of our course. Any of you who were at Dr. Costa's talk a week ago understand why that's beyond the scope of the course. He talked actually specifically about trying to make measurements in general relativity on quantum mechanical scales. It's not easy to do. So we are just measuring expectation values. We know how to do this. We know that expectation value for x is going to look like some integral from minus infinity to infinity of basically x times your probability density p of x. It could be p of x comma t if you'd like. Okay, or in other words, integral from minus infinity to infinity of x psi of x comma t squared dx. Okay, Now, we could do the integral. I'm not going to, because we can get the answer by inspection. With that said, it's a little harder to do by inspection when you don't specifically have that in front of you. So as a reminder from last time, this function, or if you prefer, this function looks like this. One over alpha gamma square root 2 pi e to the negative x minus p naught over m times t squared over 2 alpha squared gamma squared, where we defined gamma, big gamma, as square root of the modulo squared of little gamma, which ends up looking like 1 plus t over tau squared, square rooted, and alpha we had previously defined for ourselves as h bar over 2 beta, where beta was in turn basically a width function for our momentous states. All right, so okay, we're doing this integral. What's the answer going to be? Well, here's what I mean by we can get it by inspection. This whole damn thing is a Gaussian. So these are your positions. These are basically your probabilities, if you will, your probability densities. This is at x comma 0, if you want this to be 0. And essentially you have, that's going to be way too high. You have your Bill curve. As best as I can draw it. So, for this one right here, what's the expectation value? Well, by inspection, we know that the expectation value is kind of like an average. And say this thing and this thing right here, equal probability, equal distances to the positive and negative direction of x. And that's true of any pair of things that have equal distance. They also have equal probability about this point. So this right here would be the expectation value at time equals 0. Okay, so in other words, it's the center of the distribution because of the symmetry of the distribution. Now, if we decide to go to some later time t, yes, there may be some kind of changes in the width and whatever. Doesn't matter. There's still going to be some point of symmetry. I'm really bad at drawing things. Just going to draw it like this. I'm not trying to get the width right or anything like that. I'm just trying to show that it's moved over from here to here. So this becomes P of X comma T. And the question is, how far over did it move? Well, this right here is the new expectation value, X of T. And so the question that you should be asking to do this by inspection is, how far did this right here move? And the answer is it moved by, I hesitate to say delta X because we're going to want that for uncertainty, but it moved by let's say x is equal to speed at which it's moving times time, but the speed at which it's moving is these two terms right here. Okay, so our new expectation value at all times for this thing should basically look like P naught over M times however much time we've done. Where again, this P naught is lowercase p, the momentum. Okay. So, all right, cool. We got that by inspection. Whoops. What about the uncertainty? Well, the uncertainty you can kind of get also by inspection. It's basically going to be these terms right here. Okay, or these terms right here. In other words, delta x should be this term, this analogous term. And you know that this right here as a Gaussian should be 1 over this square root 2 pi e to the negative of essentially x minus expectation value of x squared divided by 2 times the uncertainty. So this term right here just becomes alpha gamma, which is h bar over 2 beta square root 1 plus 2 beta squared time over m h bar, and this term right here is squared. Remember that beta, so recall the uncertainty in momentum was just beta. That was a earlier result from last time. So that basically means that now we have a relationship between these two uncertainties. And as you can imagine, that means that we are going to look at some form or fashion of uncertainty principle. Specifically, you can recall that this right here was for momentum, and for what it's worth, the expectation value of momentum was P naught. All right.
Dr. Sanders,
Yes.
where you first have gamma defined there, I can't read that second term under the radical. What does that say?
Where I have defined gamma.
Yeah.
Oh, yeah, okay. So you are asking about this.
Yes.
Yeah, all right. Let me rewrite it a little bit more neatly, I hope. Okay, so gamma should be equal in this case to 1 plus basically the square of some time divided by some time constant parameter. So it's 1 plus t divided by tau.
Okay.
So does that mean that T over tau is equivalent to 2 beta squared T over M H bar?
Yes, that is what that means, because that's actually how we define tau to begin with.
Which portion of that term is tau? Is it 2 beta squared over MH bar?
Yes.
Okay. Or MH bar over 2 beta squared, rather.
Right. It's MH bar over 2 beta squared. And that along with lowercase gamma, which I'm not using here, were both defined in yesterday's notes, as it turns out. And that was when we were setting up our integral. So some comments, now that we have a nice cluttered page. Some comments. If delta P is beta, then we're basically claiming that the wave packet momentum width is constant. So delta P equals beta is constant. We'll call it constant packet width for short. And then we also have an expectation value of P. Oops. P is P naught. Okay, and that means that the center momentum is also constant. Excuse me. So we'll just say momentum center is constant. All right, so basically these things right here are kind of conservation of linear momentum. Now let's look at what X is doing. Well, coming up here, those were kind of our results. X of T, there's a T here. Delta X, there's some time in here. So this and this are both time dependent. So essentially, in some sense, I've drawn this backwards. It's like I said, I can't draw, but a more proper drawing of this thing it spreads out in time. Okay. I'm not going to keep that on there because it's going to be confusing after the fact. This should be wider.
This is just a comment regarding scale.
Yeah.
Are you what you're getting at is it's figure 6.9 in the book, is that right?
Yes, basically.
Okay.
Basically. Which I didn't actually necessarily label that in my notes, but I think, let's see, can I go to there it is. So by the way, I've got like real and imaginary parts,
Yep.
but here, this is 6.9. This is actually showing the difference between phase velocity and group velocity. So I'm not necessarily getting at this here.
Okay.
So this right here, this peak and this peak line up on this dark spot. So essentially what these animations, this is sort of like an animation, like one time step later, we're here, one time step later, we're here, one time step later, we're here. And if you look at where the absolute peak of the envelope is, it's tracking with this dark black dot. If you're looking at what the carrier has done, it's tracking with the open circled dot. So you have a different phase and a different group velocity.
This phenomenon is natural of all waves, though, isn't it? Like even waves in water
Yes,
exhibit
of
the same
course.
behavior. Yeah.
Yes, very much so. Very much so. And it's the group, it's basically the group which is actually carrying the sort of readable information for you. So kind of an aside, you know that we have like a universal speed limit of C naught, right? Well, that C naught actually corresponds to group velocity only. The phase velocity can actually exceed C naught because it's not actually carrying any, measurable, readable information, at least that we know of.
Interesting.
But that's a bit of an aside. I don't want to go down that rabbit hole today, or at least now. Not at this moment. Not today, really. Maybe a little later. These guys are time dependent. Wave moves, which we would expect if you have a momentum center that's constant, we kind of expect it to be moving, especially if we have a constant wave packet width. But also widens. Okay, so that's what this node is getting at, is that what really should be happening in space is you have something like this. Let's say t equals 0. And then sometime later, so we have how far it's moved. And we also have how much it's widened by. So it's wider here than here. And since it's wider, it's also necessarily shorter. Now, this is, to go to Nathan's favorite topic, this is analogous to stretching out a laser pulse. Huh?
Background noise.
Oh, okay. This is analogous to stretching out a laser pulse in time due to dispersion. So as you travel through some refractive index for a laser, so laser pulse, it's going to typically travel through something that has refractive index in or eta of lambda, or if you prefer, of omega. And so different, essentially different wavelengths or different frequencies of your light see different refractive indices. That means that they have to travel at different speeds. And that means that if everything was initially lined up, the whole thing's moving like this, but maybe one of them is moving faster than the other. And so as everything moves this way, they get spread out. Okay. And so, this is normal behavior for laser, for light, for a photon, for wave packets like that. It's not exactly what we'd call normal behavior for a classical particle. Classical particle, you have a thing that moves here and it travels like this. It doesn't expand like this as it's traveling. Okay, so we're getting some sort of non-classical behavior here. Let's go ahead and also do group and phase velocities again here. We've already kind of approached this from one way. Another way is this. Let's say group versus phase. That's such bad writing. There. So how are these things defined? Well, phase velocity is defined just as omega over k. So this is actually your v equals lambda f. Okay, and that's your carrier wave. Your group velocity, recall, is actually d omega by dk evaluated at k equals k naught, or in other words, at the peak. So eval at peak. Okay, so now let's apply these to the quantum mechanical free particle. So phase velocity, v phase, is going to be as omega over k. This right here, this is a lowercase k. This is omega, you'll recall, could be h bar omega as long as you have an h bar k down here. But that's the same thing as an energy divided by a momentum. Or in other words, a p squared over 2m divided by p. And so after you've canceled out this part, you end up with p over 2m. And that is 1/2 of your classical particle speed, or of your equivalent classical particle speed. Okay, so now let's do for the group velocity. The group should look like d omega by dk at k naught. So you can do, say, you can always multiply by a constant on top and bottom. So you can see this is going to be dE dP. This was still evaluated at k naught. This is now evaluated at p naught. And so now you have d by dP of p squared over 2m. Well, this is an easy derivative to do. You end up with d by dP of p squared, which is 2p divided by 2m. And so that ends up being p over m. Of course, we're evaluating at p naught, so you end up with p naught over m. But that's the same as your classical. And these right here, the difference between the p naught and the p is that, remember, these were supposed to be evaluated at a particular frequency at a particular momentum, specifically the carrier value. So these kind of implicitly all have knots in them as well. All right. In some sense, I've just kind of skipped ahead by answering Nathan's earlier question about group versus phase velocity on this diagram. So we've already discussed this, so I'm going to not discuss it a second time. All right. Now we know what this is all leading up to, of course. Don't we?
So the relationship is always 2-to-1, the group velocity and the phase velocity?
For this,
Okay.
it ends up having to be, yes. For this one, for this particular wave. But remember that this particular wave is not all waves. This was the totally unbound wave.
Okay.
With a continuous superposition. And it worked out also with like the 2 or 5 discrete wave or indiscrete wave, but all of those have assumed an unbound wave. That's the main thing. So what is all this leading up to? I think you guys know the answer.
You just mean like the uncertainty principle?
Right. See, you did know the answer. It's all got to lead up to an uncertainty principle of some sort. So, uncertainty principle. Specifically, we're looking now at Heisenberg's uncertainty principle for momentum and position. Well, the Heisenberg uncertainty principle says delta X, delta P has to be what?
H bar over 2 greater than or equal to H bar over 2.
H bar over 2. Specifically greater than or equal to. This is important. It's not just equal to. It's greater than or equal to. Okay, so in earlier lectures, specifically Quantum 1, really like chapter 2, we know that if two observables can't be simultaneously measured, then they don't commute and vice versa. And we basically express this as uncertainty, whoops, really bad there. Uncertainty of A times uncertainty of B has to be greater than or equal to 1/2 of the commutation A comma B, where our uncertainty delta of A or B, doesn't matter which, is square root of essentially the A minus expectation value A squared. So it's the root of the expectation value of this quantity. And that in turn was the more familiarly or regularly used expectation of the square of A minus square of the expectation of A. Okay. So the first question is, do momentum and position commute? And the answer is no. Specifically, if we were to do the commutation of these two, we would actually get IH bar. Okay, so this in turn means that this right here, in whatever order you want to go in, can't be 0, but rather that it is something else like this. And turns out that this right here, delta P, delta X, greater than or equal to H bar over 2, means H bar over 2 is minimum. That's not how I spell that word. There we go. It's the minimum uncertainty product. Now, why do we have to say it's a minimum uncertainty product? What in the previous discussion implies that it may be greater? And put differently, when is it at a minimum?
Is it at t equals 0?
That is when it's at minimum, correct. Now, why is it minimum there?
Because it's I don't know, it gets wider through time, right? Is that why?
Right. Delta P is constant. It stays the same width. The uncertainty and momentum stays the same. Delta X is time dependent. It basically widens, but it widens in the past as well as in the future from this perspective. But differently, if we come back up here and look at delta X, here at the bottom is the function. H bar over 2 beta, all right, those are some constants, times root of 1 plus a bunch of constants times time squared. Okay, so in some sense, this is saying whether time is positive or whether it's negative, you're still getting a larger value for delta X than at time 0. Put differently, if you take the derivative with respect to time of this and set it equal to 0, you will find that that happens at time 0. That's your minimum delta x. Since delta p is constant and delta x is not constant, the minimum product must occur when delta x is at a minimum. And as it turns out, that's at time t equals 0. And as it turns out, when you take the product of those two at time 0, you get h bar over 2. For what it's worth, this right here, I make a little note in red. This right here is part of your homework showing this. It's problem 6.6 in the book. At least it's problem 6.6 in my book. I think it's problem 6.6 in your book as well. It occurs to me that the downside to all of these referencing McIntyre, by the way, is that if he ever comes out with a second edition where there's more problems added, all of my problem numbering will be wrong.
Dr. Sanders, is there some version of the uncertainty principle that has a function of t applied to h bar over 2?
Yeah, this one. This one would. Because if we go back up and get both of these things, so explicitly, you have that delta p equals beta. You have that delta x, and now we have to kind of scroll up to get it, but delta x is basically all this noise. So it's h bar over 2 beta square root 1 plus, there was a time in here, but I think it's a 2 beta squared or whatever, 2 beta squared over m h bar. All squared. So if we apply the uncertainty principle here, this means that delta x delta p becomes h bar over 2 beta square root 1 plus 2 beta squared t over 2 over not 2 over m h bar squared. That's your delta x term times your delta p term, which is just beta. But now look, beta, beta. So if we combine these two, you get h bar over 2, the expected thing, square root 1 plus 2 beta squared t over m h bar.
That makes it pretty clear.
Squared.
Yep.
And so you can see if we plug a 0 in for t here, what happens? Well, this whole term becomes 0. And so you're left with square root of 1, which is just 1. And so that means delta x delta p is h bar over 2. What if we plug in some other value for t? For example, maybe we plug in t equals tau, or in other words, t equals mh bar over 2 beta squared. Well, then we have h bar over 2 square root 1 plus this whole thing becomes 1 squared. So that is root 2 over 2 h bar. That's bigger than h bar over 2. We have more uncertainty at this later time. And so on. You can plot this. I did not. I don't recall McIntyre plotting it either. But you could in principle plot it and see like what does the uncertainty look like? You know, what's the uncertainty product look like as a function of time? And you know, the minimum value will be h bar over 2, and over time it just spreads out. And in fact, at very long times, it basically becomes linear. So it'll be kind of nonlinear near that local trough. And then for very long times, it becomes just linear spread. There are some minor notes in here about the Fourier connection between your uncertainty, or the Fourier connection to the wave packet for uncertainty. And what it comes out to is that if you include all this shaping stuff with side modes, discrete and everything like that, that what you end up getting with is delta x, delta p is pi h bar, for what it's worth, at minimum. So that also satisfies this need to be greater than h bar over 2. I'm not going to explicitly do that because we're sort of out of time on the day. So I think I'm going to stop there. Unfortunate for future classes. All right, so we're recording. Now we're ready. Where we are starting from is that I got to remember to share again because I had to unshare to record. There we go. Is a little bit about these Gaussian wave packets and waves and particles and so on. So this is figure 610 from your book, which I guess you could read from the title of the figure. And they're basically, he's kind of defining things as wave, particle, particle. And what he basically means by that is if you look at the real part of psi of x for what he's labeling as like wave, there's many cycles of your carrier frequency in here, but you have a fairly narrow range of momenta. And in fact, if you stretched out this wave so that it had an infinite duration, you could in fact have one momenta here. Duration really in this case is wavelength. If delta x approaches infinity, then this approaches your delta function spike. So because we have a really narrow range of momenta, we're calling it a wave, and it's, you see quite a few cycles within your wavelength. Then he calls this region where there's like a handful of cycles the wave particle, where it's maybe wave-like and maybe particle-like, and slightly broader in momentum than before, slightly narrower in spatial extent than before. So it's kind of like an intermediate state between these two. And then particle, what he's labeling as like particle, means it's pretty well localized. This thing is pretty well localized. It's very narrow peak here, very few cycles of whatever your carrier is will fit within this peak, but you have a correspondingly broad range of momenta. Okay. And so, your absolute extreme cases would be either a spike here in momentum, in which case you have largely a single sinusoidal, non-decaying position function. Or you could get a spike in your position, your real part of your psi of x. In which case, in some sense, this right here becomes infinitely broad. Okay. And for what it's worth, your infinite spatial extent single wave would correspond to the following mathematical function. Sorry, all my chords are kind of tangled up here. So single, let's call it pure wave. This would be momentum single, momentum state, or if you would prefer, this would be a momentum eigenfunction. So this would look like this. Again, we're doing X representation, but it is a momentum eigenfunction. And let's do this proper. 1 over root 2 pi h bar e to the I p naught x over h bar. So now we say, what does Fourier analysis have to do with this, or have to say about this? So we could write something like the same eigenfunction, but in momentum representation should look like the Fourier transform, which is usually some fancy looking f of the original state in X representation. And so of course that would look like an integral from minus infinity to infinity of our original state. Times e to the minus I px over h bar dx. And then this is also over 2 pi h bar. Okay, and so combine this part right here with the same thing in this original equation up here. This basically means that we're expecting this to look like 1 over 2 pi h bar minus infinity to infinity. And then we have e to the I p naught x over h bar, e to the minus I, and then just p times x over h bar. And so if you combine those two things, this and this, the main difference is in this term right here, p versus p naught. And so this ends up being 1 over 2 pi h bar integral from minus infinity to infinity, e to the I, we could say p naught minus p x over h bar dx. And essentially what you then do is kind of go to your integral tables and make use of, well, what the integral of this should give us from minus infinity to infinity. And the answer is this should just look like the delta function of p minus p naught. So that is a pure pure momentum function. It has a non-zero value only at p equals p naught. And so that is why this allows us to have it as a single eigenfunction. Okay. But differently, this function could be recast in terms of signs, which is specifically that it is like a sine of ax times sine of bx. So you have 1 over root 2 pi h bar. And that's how you find it in the integral table. Fourier transform of a sine wave is Dirac function. So now we say, what about the pure particle case? Okay, that means that this should be an eigenfunction or an eigenstate x naught. Okay, and that in turn could be represented by phi sub x naught of x. And that in turn should look like the delta function of x minus x naught. Okay, so this would satisfy your position eigenvalue equation. So position eigenvalue equation is, of course, something like position operator acting on position eigenstate should be some value for position times position eigenstate. Okay, and that is equivalent to this right here. Oops, it's not quite how I wanted to write that. That is equivalent to this right here. That makes a little more sense. So let's take the Fourier transform of this thing. So basically what we're looking for is, what is this state but in momentum representation? So again, you do the Fourier transform, and now it's of this eigenstate position. And so as before, you have your 1 over root 2 pi h bar integral from minus infinity to infinity of the thing you're trying to transform times what we've been calling transform function. And now it's dx. All right. And so this guy right here, of course, just is this up here. And so we're basically integrating over this entire all of space a delta function. But you know what that integral ends up basically having to do. It essentially transforms to just one of whatever. And so in this case, our whatever is this. So this integral ends up looking like you can include everything out here, 1 over root 2 pi h bar. Apparently I can't write infinities today. There. Okay. So comment in both cases. A momentum eigenstate and a position eigenstate both have this in common. They can't really be normalized, and so they can't really represent on their own a physical state. This is not a normalizable function. And likewise, this is not a normalizable function, not truly normalizable. And so on its own, it's not going to represent a physical state for this unbound particle.
And you should
And
have the there should be like the 1 over square root 2 pi h bar there too, right?
Yes. It should also have an over.
Like that equal sign is just for the integral.
Yeah.
Okay.
So if you want to include the everything inside the integral, you've got this as well. Yeah,
Okay.
correct.
Okay.
So there's kind of a little summary that we could do, and I'm going to cheat for this summary. I'm going to try something. Well, maybe I'm not going to cheat. I don't know. We'll see if it'll let me cheat. Here we go. I'm going to cheat. I'm just going to see if I can. There we go. So here's sort of like my pen and paper summary of what we've done so far for what it's worth. And yeah, you can see that this is slightly nicer version of the same handwriting that I'm using in these notes. This is what happens when I can see what I'm writing, where I'm writing it. But that's your summary. I'm not going to linger on this for long because, again, I post all these onto the Canvas. Actually, before I go on, though, some comments. Okay, so we can see that these eigenstates of position and of momentum in these two representations, they do demonstrate a few parallels with each other. And the same, for what it's worth, is true of the operators. You know, the bottom half is the operators. The incompatibility of position and momentum via Heisenberg's uncertainty does stand in somewhat sharp contrast to how independent these two things are in classical mechanics. So one quantum mechanical thing that we see here is this uncertainty principle. You know, in classical mechanics, you can say this particle is located at this position and it has this momentum. But in quantum mechanics, these two things, position and momentum, they're complementary quantities. And so what that means is that if you swap from one basis to another, position in momentum in position or position in momentum space, they are derivatives of one another. So position in momentum space is going to be a derivative of momentum. Momentum in position space is a derivative of position, the difference being the minus sign or not the minus sign in front of the IH bar. And then these two eigenstates end up being Fourier transforms of each other. The end result of all this, of course, is that in quantum mechanics, we can't really know an exact trajectory for a particle, because that would require that we know where it is at all times, and that would also require that we know what its velocity, hence momentum, was at each point in time. So you'd have to know exactly both, which is not compatible because of the uncertainty principle. Now, Dr. McIntyre in his text goes through this very rough energy estimation problem. And it's really like, can we get within something like an order of magnitude? And not even then. Like, I think you end up with a factor of 40 difference between sort of estimate and then the real what should it have been. But it is an estimate of essentially how much energy do you have for the minimum state for a bound state versus an unbound one. And it's there. You can read about it. I don't really want to go through that calculation. It's an incredibly rough estimate. So I will skip that. It turns out, though, that the consequence of not doing that thing is that we are sort of on to my next set of notes.